Good morning, everyone. Thanks for joining us today and welcome. I am Richard, the CEO and a co-founder of Adiona. This session is called AI and Machine Learning in Logistics and Delivery. And it's meant to take a really quick look at what is useful, what AI and machine learning specifically can be useful for in delivery logistics, and also a really quick look at what is being rebranded as AI and machine learning, but is really focused on traditional data science techniques that anybody can access. There are some issues in the industry right now where some people think that the outcomes that you can get from AI and machine learning are up behind a wall, where experts need to be able to deliver them. But we believe that actually a lot of these techniques are accessible to anyone in the right circumstances. And AI is more of an enabler and an amplifier of these techniques rather than always being something that is useful on its own. So it's the combination of different techniques, different data science techniques, operations algorithms, and research that really can drive the needle for you and for us. And let's just set some context. AI and ML are super, super useful in our industry. You can leverage them for some incredible outcomes that weren't necessarily achievable very easily with traditional data science techniques. And then again, using those traditional techniques, but combined with best-in-breed operations algorithms and AI, can really be where the convergence of outcomes come from. So let's look at some examples of where we and our colleagues are using AI and ML to create better optimization outcomes. Okay, so gig economy work, it's a very popular solution for last-minute on-demand deliveries. Traditionally for all sorts of things, ranging from flower deliveries and pharmacy deliveries to alcohol, last-minute parcels, high urgency things. And one of the classic problems with gig economy marketplaces is that the demand is very unpredictable, very, very difficult to predict outside of some basic trends. So alcohol delivery, classic trend is that on Friday afternoon, a lot of businesses start putting in orders for impromptu office parties or last minute planned office parties. And so the fleets tend to get really, really busy on a Friday afternoon into a Friday evening. Now that's easy to predict with historical data, but what's difficult to predict is the movement of those gig workers to keep them engaged and keep them on your platform. Because as soon as you stop delivering with one gig worker, they're going to either go back to another platform or they're going to stop working when they can't be making any more money. And as we know, they're on multiple apps, multiple sources of work, multiple marketplaces. So ML can be used to look at the historical data and figure out where the orders are coming from and the trends associated with where those orders are coming from. And then AI techniques can actually create models that will predictively place workers, suggest where workers should be in advance of those peak times. And that's valuable, obviously, for a number of reasons in terms of right-sizing the workforce and making sure that people are where they need to be at the right times. So medical and dental, this is a really interesting one as well. So there are all sorts of specialist delivery businesses that bring equipment, spare batteries, surgical tools that have been sterilized, all sorts of things back and forth between hospitals and distribution centers or hospital to hospital. It's a bit similar to gig economy, but it's even more complex because there tends to be a much wider range of time windows that need to be suited. So you may have a patient on the table urgency of a delivery that needs to be similar to a gig economy workforce that's on demand. It needs to be done urgently. Or you may have wider 4-hour windows for things that aren't so urgent but need to be same day. And likewise, you may have next day delivery as well. So how do you account for the patterns and historical records of the orders that have been delivered before And what we know from these types of things is that it can be very difficult to infer where to place the delivery resources, where to place the inventory. And a lot of it is driven by specific surgeons at specific hospitals. So if a surgeon operates out of a specific hospital on one day, and they are very much a more on-demand delivery type of professional, you're going to see a bump in your requirements for that hospital on that day. But typically those things aren't linked. You don't have a link between the rostering in the hospitals to the procurement teams that are ordering these on-demand items. And so AI and ML can be a really valuable and high impact way of linking those things together and not needing to link the rostering system. It's the AI that will figure out that you're seeing the same items delivered on different days to different hospitals and make the connection that those might be related to a specific surgeon, and then be able to predict what they're going to order and when, and then help you optimize the fleet and delivery resources, right? Another one is for hotels and hospitality and restaurants. We see specific patterns around how table linens are collected and replaced at restaurants. So for instance, since most of these fleets are working Monday to Friday like everyone else, but restaurants are very busy over the weekend, there's an urgency around picking up table linens and linens from hotels and things like that on a Monday, and needing to be replenished on a Monday as well, because they've done a lot of work over the weekend. Whereas that can vary from place to place, seasonality, and the type of establishment. So again, this is an opportunity for AI to predict those things. And then the example we'll show you today in terms of a great application of AI that we're piloting with some of our customers right now is around incorporating human decision-making into traditional route optimization. So by being able to take data from the field and from the schedulers and the routers and dispatchers and figure out where things have changed from the plan, and then creating closed loop feedback, the AI models can actually learn what changes and why without actually needing to specify all of that up front. And as any of you know who've worked with route optimization before, it can be very configuration heavy. There's a lot of specific settings that need to be accounted for. And so this helps to streamline that process and automate a lot of it. So let's look at what I promised you, which is some information around what is AI, what is ML, and what is data science, okay? So let's start at the left with what traditional data science can do for you. And it can do a lot. And we see as the majority, I'd say, of inventory predictions, of staffing predictions, of seasonality analyses are primarily still being done by these traditional data science techniques. And unfortunately, some of these are just being rebranded as being AI-powered or ML-powered, and they're really not necessarily related to those fields, those other disciplines, but they are still important. And again, where AI can come in with these traditional techniques is using them as part of its own toolbox to do more and to get better results, okay? And so where we transition from traditional data science into machine learning being a sub-discipline of AI, it's something that's kind of a mandatory type of data science for AI to work. Machine learning looks at other techniques using what we used to call big data to come up with models and representations of things that happen to those with that data. So when we talk about, again, that on-demand gig work, staff placement, it's machine learning that's going to drive a lot of the learning that's needed to do those types of things. And again, it will also rely on some traditional data science techniques. And then when we transition over into AI, this is where we talk about automation. So it's the ability of a model to learn on its own and improve on its own. In order to do that, it really requires neural networks, and there's many different types of neural networks that do different things. But at the end of the day, it requires those networks to be built and trained, and then it can incorporate other types of data science techniques and determine when and where to use them. And that's where it becomes really powerful. It's an AI with its own toolbox that then will drive better outcomes using other tools. So let's look at an example from our world. And this is a really particular example that we'll show you on the left from routes that have been created by our commercial optimizer, and each of those shapes is a delivery route. If you were to drill into those, each one of those has 50 or 100 stops for one vehicle, and that output from the optimizer is really good and it works. But if we look at how a route planner has then gone and modified those routes and changed them before actually dispatching them to the driver, we see they look like what's on the right. And what you can see, and you'll see it when I say it, maybe you won't see it because it's not necessarily obvious to somebody when they first look at it, is they've adjusted some of the routes to both reduce the number. They've gone from 6 routes down to 5. And then they've also elongated the ones in the east to kind of go along these major road corridors. And that's a very reasonable thing to do. It does not necessarily increase the efficiency though. And so the optimizer algorithm wouldn't necessarily make this choice because it's not going to be more efficient numerically. It's not going to reduce kilometers. It's not going to reduce time. But it's something that the expert human route planner will do because it makes it more drivable. It makes it friendlier for the driver to stick along those corridors and have a similar territory every time to modify commercial route optimized routes. Now, what we see is in doing that, by elongating them along a highway corridor, we call that a facilitator. So that highway is a facilitation of deliveries. It makes the deliveries possible by providing a road to go down. And we also have things that are obstacles. So for instance, the Parramatta River in Sydney. Quite often, even if it's more efficient, drivers will not want to cross over the river because it seemed to be less efficient and it seems like wasted kilometers going back and forth over a river. Again, not necessarily the case numerically, but if we want to cater to the human preferences that are, again, really important in driver retention and overall satisfaction with how this operation works, we have to consider those. And then we have to adjust the algorithm based on those facilitators and those obstacles. So how we do that is to first use machine learning to figure out what those influential factors are, the facilitators and the obstacles. And machine learning is really, really valuable at figuring out where these different types of things are and how they interact and impact the routes, the actual delivery routes. So traffic lights, street count, the density of the streets in an area is very influential on how many different routes there are potentially to go and what kind of traffic is going to be there. The speed limits on those roads and the height clearances, whether or not there's tolls and whether or not you want to avoid them. That's a pretty classic one. And then, of course, as we mentioned, things like geographical obstacles, those facilitators and those obstructions that are really going to change how humans want to interact with the delivery routes. And what we see is that once we have labeled all those things using machine learning, you can then give them to an AI model. And the AI model can then start to figure out, how would a human do this? How can I mimic what the changes the human made are by looking at all those changes? And here at Adiona, we've got millions and millions of deliveries that have been powered by the platform. We keep track of every one and collect thousands of data points for each one, and then feed that back into the AI, along with thousands of hours of human interaction. So we're also logging and collecting this information about how the dispatchers, the routers, and the drivers change the routes after they've been created by the commercial solver. And then using all of that information, we use that to train AI to mimic what the humans would do. And you can see in this example, again, same example, same territory, same number of routes. You can see on the left the original, which was 6 routes. You can see what the dispatcher did to change them in the middle panel, which you already saw. And then you can see what this AI model would do. Again, minimizing from 6 routes down to 5, elongating them to be along corridors. And you can see it's done it differently than the human would do, but it's starting to go in that same direction. And a human router may still look at that and say, you know what, it ticks the box of making it more human friendly. The drivers are going to like it, and so therefore I'll accept it. And so the goal isn't necessarily to mimic exactly what the human router would do. It's to mimic the spirit of what the human router would do for that drivability component. And if we look at a bigger example, and this is downtown Melbourne, and you look at where the river is. On the left, you see the original routes from the commercial optimizer, and some of them cross the river. And then you see what the actual drivers did and what the router and the driver decided to do. And then you can see on the right what our AI model did to improve the routes, again, not crossing the river, tighter clustering, and elongated along some of the main corridors. So that provides an output that is much more drivable and acceptable for the team. It's much more operationally focused for what the team wants to get. And it's also still very, very efficient. I think that's another key component, is that we're not sacrificing much efficiency to do these things, but the trade-off is maybe a tiny bit of lost efficiency numerically, but a big boost in drivability, driver morale, dispatcher compliance, and all the other things that make these tools much more well-liked inside the organization. Thanks, David. Saw you typing in the chat. Appreciate the question. So David has asked, how long or how big of an amount of historical data did we need to produce that AI result? Excellent question. And one of the exciting things about some new AI techniques is that it's minimizing the amount of historical data required to produce good results. In this particular model that we've developed, we only really require about a month's worth of data to get a basic result, to get something that's really, really usable. And then obviously, if we want to factor in things like seasonality, seasonal peaks, and whatnot, then it still requires a whole year's worth of data. But the actual amount of consolidated data needed in terms of size is very small compared to traditional machine learning techniques. And the sooner that we start working with a customer to start collecting that closed loop feedback in the right format, the model's training time is sometimes minutes. It's actually really, really fast process to train it. And these models that I showed you today do need to be trained on a per region, per client basis. So we are still a ways away from having some silver bullet, one size fits all model that can be used for any customer, any type of organization in any place. This is really about fine tuning it to each client's fleet, type of products that they deliver and type of service and SLAs that they require. But again, like I said, doesn't really require a huge amount of data and can be trained really, really fast. See, we've got another question incoming. Chris, thanks for the question. Says, with what you've just said, Rich, is there crossover between customers with the machine learning, or is it just client specific, which I was talking a little bit about? And he says, or are the learnings learned between customers passed on with your program? Great question. So while the fine tuning is generally customer specific, there are a lot of industry crossover things that are universal. And so the model does already have pre-trained information around the geographical constraints or things like that that are applicable across any industry, any clients. And so those basic things around that I showed you around facilitators and obstacles, those are universal. So those are pre-built into the model and don't need to be reinvented every time that we work with a client on that. It's really more the details around the SLA compliance and the types of product and the fleet specific things that need to be tuned per client. But we are developing a set of best practices that allow us to make this process faster and easier with each type of new client if we've got one already with a similar type of vertical, similar type of product that they're working with. And so thanks for that. And David has a question, different David, have LLM or VLM been used to have more smarter reasoning yet? That's an interesting question, especially off the back of the new OpenAI model that's just been released, that, the O model, that strawberry model, as they're calling it, that's intended to have extremely more reasoning. It's an interesting thing because more reasoning doesn't necessarily equate to better results in these scenarios, and especially because, to be honest, road networks are relatively simplistic in terms of complexity for AI. They're static things with static parameters. They don't change very quickly, so therefore it's more straightforward for an LLM to work with road networks. It's really more about learning and reasoning around why things have changed operationally, where I think LLMs have a bit more opportunity to grow. So these examples still relatively simplistic models that are used, but I think that there's an opportunity when we start to tie these things together upstream from delivery. And what I mean by that is inventory prediction, warehouse management, manufacturing, all the other links in the supply chain where the variables do start to change dramatically. There are many more of them, and more reasoning capability will help to get better results in those types of upstream complexities. And that's something that I think is coming in the next couple of years. With that, I think we'll wrap up, finish up. So thanks everyone, and